Ordinary cranes can lift a few tons, but in the deserts of Qatar, a single hoist went wrong and nearly shut down a $15 billion refinery, until a German machine towering over 100 meters, the Tadano Demag CC 8800-1, pulled off a 1,400-ton lift that risked catastrophic collapse if a single piston failed. Cities like Berlin and Hamburg faced their own impossible challenges, moving domes through medieval streets or raising turbines higher than any crane before, with lives, millions, and reputations at stake. These are the real stories behind the 3 biggest German cranes on Earth, and why their triumphs, built brick by brick from fear, innovation, and raw steel, changed how we build everything. But just how close did these giants come to disaster? And what lessons did they force engineers to learn the hard way? Standing in the heart of a refinery or perched on the edge of a wind-blasted desert, the Tadano Demag CC 8800-1 looks less like a crane and more like a moving skyline. Its official capacity, 1,600 metric tons, puts it in a league where the numbers begin to feel abstract. But the math is real. With its boom booster kit, the CC 8800-1 can nearly double its rated strength at long reach, bringing the theoretical maximum to 3,200 tons in twin configuration. That's enough to lift a fully loaded passenger jet, twice. The main boom stretches up to 156 meters, and with a luffing jib, the hook can reach 240 meters into the air. The power comes from 2 390-kilowatt diesel engines, each one strong enough to drive a city bus. Every movement, hoist, swing, crawl, is controlled by a network of hydraulic pumps and steel cables, with load moment indicators monitoring every ton. When the CC 8800-1 arrives on site, it doesn't roll up in one piece. It arrives as up to 70 separate truckloads, boom sections, counterweights, superstructure, crawler tracks. A 10-person crew can assemble the entire machine in about 10 days, even under the sun and dust of the Gulf. The real secret lies in the load chart. At a 20-meter radius, the twin configuration can safely hoist 3,200 tons. The standard single boom setup, without the boom booster, maxes out at 1,600 tons. But with the booster, an extra lattice structure bolted to the main boom, the capacity at long radii jumps by as much as 90%. That means a column that would have needed 2 cranes or required dangerous tailing maneuvers can be lifted in one go. The counterweight system is modular, 135 tons of base slabs, plus up to 780 tons in additional plates, stacked and configured depending on the lift. Every parameter is calculated before a single pin is driven home. The crane's IC-1 control system tracks wind speed, boom angle, and weight distribution in real time. If the wind gusts above safe limits, usually 7 meters per second, the system forces a pause. Even the rigging is oversized. 4 main winches, dual luffing winches, and quick connect rope ends, all designed for rapid reconfiguration. This machine is not just about brute force. Its modular design means it can squeeze into tight industrial sites, reconfigure overnight, and adapt to the shifting demands of modern construction. In the world of heavy lift, every ton, every bolt, and every meter counts. The CC 8800-1's numbers are more than statistics. They are the difference between routine success and a billion-dollar disaster. At the Al Zour refinery in Kuwait, the CC 8800-1 faced a test that would not be solved by engineering alone. The plan was straightforward on paper. Lift a distillation column weighing over 800 tons, more than 65 meters long, and set it in place before the desert heat could turn steel into a hazard. By mid-morning, The temperature had already climbed above 50 degrees Celsius. The air shimmered, the ground radiated heat, and the crew's boots left prints in soft, sun-baked sand. Hydraulic lines groaned as the main boom crept into position. The control system reported no faults, but the rigging foreman, 30 years on cranes, never lost a man, watched the pressure gauges and felt something off. The hydraulic fluid was running hot. Too hot. The sensors read within limits, but the lines themselves pulsed with a telltale vibration, a sign that pressure could spike without warning. The schedule called for the lift to proceed. Every hour lost meant tens of thousands in idle costs. But the foreman called for a full stop. No debate, no vote. He ordered the crew to bleed the lines, flush the fluid, and wait for the sun to dip. Some grumbled, others checked their watches. The pause lasted nearly 2 hours. In that time, the column sat cradled in its rigging, heat radiating from its skin. The site manager radioed for an update every 15 minutes. The foreman listened to the pump's whine, checked the fluid temperature, and waited for the numbers to drop. When the lift resumed, the hydraulics responded with smooth, even force. The column rose, swung over the lattice of pipes and scaffolding, and settled onto its base with less than 3 centimeters of drift. Later, the operator would recall how close they'd come to disaster. A blown line under load could have dropped the column or injured half the crew. Instead, the only casualty was the schedule. The lesson traveled fast. Machines can be rebuilt, but there's no replacement for a foreman who trusts his gut. In the world of megalifts, precision isn't just about numbers. It's about knowing when to pause, even when every clock on site says go. On a city street lined with scaffolding and police barricades, the Liebherr LTM 1200-9.1 arrives not as a single machine, but as a convoy. 9 axles, each one steering independently, snake around tight corners that would stop a crawler dead. This is Germany's largest mobile crane, 1,200 metric tons of lifting power, highway legal, and built for the kind of jobs where no crawler can go. The heart of the machine is its telescopic boom, a lattice of high-strength steel and carbon fiber sections that stretches up to 100 meters. With a lattice jib extension, the hook can reach a staggering 188 meters, tall enough to clear the roof of almost any building in Berlin. The secret to this reach isn't just raw material, it's geometry. The boom is stabilized by a Y-guying system, 2 high-tension cables that fan out from the boom tip to massive anchor points on the chassis. This Y-shaped bracing allows the crane to lift heavier loads at greater heights without adding more axles or ballast. Carbon fiber inserts in the guying system cut weight without sacrificing strength, a solution born from months of debate at Liebherr's Ehingen plant. Engineers argued over every kilogram, running simulations until the design could handle both wind and the sudden jolt of a swinging load. Counterweights, up to 202 tons, are stacked on the rear, but the real advantage lies in the outriggers. Each one telescopes outward, pressing into the pavement with a force that would crush a city car flat. Sensors buried in the pads measure ground pressure in real time. If the numbers drift out of range, the crane's Licon 2 control system flashes a warning on the operator's dashboard. Every movement, boom extension, slewing, hoisting, is tracked and logged. The computer knows the weight, the angle, the wind speed, and the exact position of the hook at all times. The operator sits in a cab that feels more like an airplane cockpit than construction equipment. 2 engines drive the machine, a 550 kilowatt diesel for the carrier and a 300 kilowatt unit for the superstructure. The controls are fly-by-wire, with redundant circuits in case of failure. A joystick nudge can move the boom tip by a few millimeters or swing it 90 degrees in a single smooth arc. If a gust hits, the Licon system reacts instantly, locking the movement until conditions stabilize. Urban lifts demand more than reach. They demand precision. The LTM 1200-9.1 can thread its boom through a maze of tram wires and traffic lights, then extend upward with the kind of control usually reserved for surgical robots. Y-guying lets the crane hold a heavy load steady at a 70-meter radius, where most machines would tip or sway. The real magic is in the numbers. At full extension, the margin for error shrinks to centimeters. The computer and operator work together, adjusting for wind, load swing, and the unpredictable chaos of a live city. No crawler, no matter how large, could navigate a city center or set up on a street grid this tight. The LTM 1200-9.1's mobility, backed by its boom geometry and real-time monitoring, makes it the only tool for the job when the skyline itself needs to be lifted, one piece at a time. Night falls over Berlin, but the work is just beginning. The Humboldt Forum Dome waits on its rigging, gilded steel catching the glare of streetlights and camera flashes. The crane, a 9-axle Liebherr, its telescopic boom already stretched high above the city, stands at the center of a cordoned plaza. Police hold back curious onlookers, while city officials check permits and radio updates to traffic control. Every minute the street stays closed costs the city thousands, but there's no room for error. The dome itself weighs nearly 40 tons. The lift radius is over 30 meters, pushing the boom close to its safe working limit. The crane's Y-guying cables are tensioned, spreading the load like a suspension bridge. Sensors in the outriggers and counterweights feed live data to the operator's cockpit. The margin for error is less than 2 centimeters, about the width of a thumb. A gust of wind sweeps through the plaza, rattling scaffold poles and sending a ripple through the crowd. The anemometer spikes above 7 meters per second. In the cab, the coordinator calls for a halt. The operator's hands freeze on the controls. On the ground, riggers signal the all clear, but the order stands. No one argues. The city's regulations are strict. If the wind exceeds the threshold, the lift stops, no matter how tight the schedule. The weight drags on. The dome hangs suspended, swaying gently. Police shuffle in the cold. A city planner checks his watch, muttering about the cost of overtime. But the coordinator doesn't budge. Years of experience have taught him that the only thing worse than a delay is a mistake. The dome's shape acts like a sail. One wrong move, and the load could swing out of control, endangering workers and bystanders alike. Finally, the wind drops. The anemometer settles below the limit. The coordinator gives a nod. The operator eases the joystick forward, and the dome rises, slow and steady, guided by laser markers and hand signals. The entire plaza seems to hold its breath as the load inches upward, clearing the scaffold by millimeters. At full extension, the boom flexes, but the Y-guying holds firm. The dome drifts into position above the waiting structure. Spotters call out corrections in short, clipped phrases. The crane's computer adjusts for every shift. Wind, load swing, thermal expansion. The dome settles onto its base with less than 2 centimeters of drift. A cheer goes up from the crew. The coordinator allows himself a rare smile. Later, city officials will cite the operation as a model for urban heavy lifting, permitting, safety, and precision all working in concert. But for the crew, the memory is more personal. In the heart of Berlin, under the glare of the city and the pressure of the clock, the decision to pause made all the difference. The dome stands today not just as a monument to history, but as proof that in the world of megalifts, control is everything, and sometimes the hardest move is knowing when to wait. The Liebherr LR 13,000 stands at the edge of what's possible in heavy lifting. Its maximum capacity, 3,000 metric tons, pushes the limits of steel and engineering. The main boom reaches 144 meters, with a luffing jib extending another 54 meters, making the hook soar above most city skylines. But the real secret lies in its ballast system. Up to 1,500 tons of containerized counterweight, delivered piece by piece, each slab tracked by RFID for precise control. This isn't just brute force. The crane's twin 1,000-kilowatt diesel engines, together producing 1,360 horsepower, power the slew ring, winches, and crawler tracks with relentless consistency. The boom is built from lattice segments, each section tailored, lighter at the top, stronger at the base. To balance weight and strength, every lift begins with load charts, mapping out safe limits for every configuration, from main boom to superlift. At a 12-meter radius, the LR 13,000 can hoist its full 3,000 tons. At maximum height, the safe load drops, but still eclipses any other crawler crane. The LICCON control system monitors wind, load, and ballast in real time. If conditions shift, it can halt the boom or lower the load safely. Moving the LR 13,000 is a feat in itself. Over 200 truckloads, weeks of assembly, and a ballet of crews fitting every cable and bolt. Once raised, it becomes the benchmark for refinery lifts, power plants, offshore modules, and world record tests at Ehingen. German engineering, tested at the highest level, ready for whatever challenge comes next. At the Liebherr factory yard in Ehingen, the LR 13,000 stands assembled at its full height, 248 meters from crawler to hook. The air is still, but every eye is on the anemometer. Wind speed hovers between 4.2 and 5.8 meters per second, just below the 7-meter cutoff that would halt the test. Triple sensors feed live data to the control station, where the test engineer watches each decimal tick. Crew radios crackle with updates from ground to tip. No one moves without the green light. The test isn't just about height, it's a trial of the crane's slewing ring, an innovation that lets the entire superstructure rotate under massive load, even at record elevation. Ballast trailers sit ready, hundreds of tons balanced at the far edge of the yard. The engineer studies the wind, then gives the call. The boom begins its climb, luffing jib reaching for the sky, section by section. At 200 meters, a gust rattles the cables, 6.4 meters per second, still safe, but close. The order comes, pause. The crew waits, silent, as the wind dips again. Only when the anemometer steadies does the lift resume. Every meter adds tension. The boom flexes, telemetry screens flicker with live load data, and the ballast system shifts to counter the slightest sway. At full extension, the hook hangs 248 meters above the gravel, a world record for a crawler crane. Relief ripples through the crew. The test engineer notes the readings. Wind within limits, slewing ring stable, no alarms. For a moment, the world's largest crane holds its breath, perfectly balanced between gravity and trust. The LR 13,000's 248-meter hook height, verified in the 2013 Hamburg wind test, stands as the tallest ever achieved by a conventional crawler crane. Throughout this documentary, we've seen how the Tadano Demag CC 8800-1, Liebherr LTM 11200-9.1, and Liebherr LR 13,000 redefined what's possible in lifting. Whether placing 1,500-ton refinery columns in 50 degrees Celsius desert heat, or maneuvering a 35-ton dome with just 2 centimeters of tolerance in central Berlin, yet some details, like the full cost breakdowns of wind test logistics or the precise redundancy protocols, remain undisclosed in official documentation. What is clear is that these machines have changed global construction, enabling safer, faster, and more precise assembly of power plants and infrastructure. According to published project records, their modular designs and advanced monitoring systems now set industry standards worldwide. As of today, No other country has produced a crawler with a higher certified lift or reach. The story of Germany's biggest cranes is, above all, a record of engineering pushing practical limits and of human decisions that make every impossible lift a reality.